At 7:59 p.m. Eastern Time on April 10th, every monitor and mission control displayed the same condition, not a malfunction, not an equipment failure. The Orion spacecraft, carrying 4 crew members traveling at 25,000 miles per hour, had entered the plasma blackout. For the next 6 minutes, no signal would leave that capsule. No command could reach it. No intervention of any kind was possible. The heat shield surrounding the crew had fractured in more than 100 locations during its previous flight. NASA had documented this. The crew had been informed, they boarded anyway. What occurred between 7:59 and 8:05 p.m. on April 10th, inside a capsule encased in plasma at 5,000 degrees Fahrenheit, is the subject of this reconstruction. On April 1st, 2026, at 7:24 p.m. Eastern Time, the Space Launch System rocket lifted off from Launch Complex 39B at Kennedy Space Center in Florida. The launch was nominal. The trajectory insertion was nominal. The vehicle performed without significant anomaly. Aboard the Orion spacecraft, designated by its crew with the call sign Integrity, were 4 individuals whose collective assignment was not to land on the moon, but to demonstrate that the systems required for a crewed lunar landing could survive the full return journey from lunar distance. Commander Reed Wiseman, a former Navy test pilot, veteran of 1 prior spaceflight to the International Space Station, selected to lead the first crewed lunar mission since the Apollo program concluded in 1972. Pilot Victor Glover, the first black astronaut assigned to a lunar mission in the 53-year history of human spaceflight beyond low Earth orbit. Mission specialist Christina Koch, holder of the record for the longest single spaceflight conducted by a woman in NASA history. Mission specialist Jeremy Hansen of the Canadian Space Agency, the first Canadian and the first non-American to travel beyond low Earth orbit. The mission profile for Artemis II was a free return trajectory, outbound to the moon, a powered fly bringing the vehicle to approximately 4,600 miles beyond the lunar far side, and return. The crew would not enter lunar orbit. They would not descend toward the surface. The purpose of the mission was the return itself. 695,000 miles total, farther from Earth than any human crew in history. The 10 days in transit proceeded without the critical anomalies that had complicated earlier phases of the Artemis program. What the transit period did not resolve, what it could not resolve, was the question that had been present since before the launch date was confirmed. The Orion heat shield had a documented problem. The return from the moon would test whether the solution implemented to address that problem was sufficient. Getting to the moon, in engineering terms, is a propulsion problem. A sufficiently large rocket with adequate fuel and a calculated trajectory can place a vehicle in lunar distance. Getting home is a thermodynamics problem, and the history of human spaceflight has demonstrated, on more than one occasion, that thermodynamics problems are unforgiving of incomplete solutions. The approach to the return trajectory for Artemis II did not follow the methodology used on Artemis I. The reason for that change is the subject of the next section. In December 2002, an uncrewed Orion capsule, the same vehicle design that would carry the Artemis II crew, completed the Artemis I test mission. It entered the atmosphere, executed its reentry profile, and was recovered. Post-flight inspection revealed a finding that engineers had not anticipated. The Orion heat shield is composed of AVE-coat, an ablative thermal protection material with direct lineage to the Apollo program. Ablative materials function on a specific principle. Rather than absorbing and retaining heat within the vehicle structure, they sacrifice the outer material itself. The AVE-coat chars, oxidizes, and erodes in a controlled fashion, carrying thermal energy away from the vehicle as it burns. The approach worked on every Apollo mission that preceded Artemis. It was the established methodology. What the Artemis I inspection found was not the controlled, predictable ablation the simulations had projected. Engineers cataloged more than 100 separate fracture locations in the AVE-coat material across the heat shield surface. The char layer had failed at points the pre-flight models had not identified as high risk. Material had been lost outside the projected parameters. The cause, following analysis, was identified as a specific interaction between the Artemis I re-entry trajectory and the thermal decomposition process of the AVE-coat material itself. Artemis I had used a skip re-entry profile. The capsule enters the upper atmosphere at a shallow angle, decelerates partially, briefly bounces back into the upper atmosphere. The physical principle is identical to a flat stone skipped across water, and then descends for the final re-entry. The maneuver is designed to distribute the thermal load over a longer duration, reducing peak heating at any single moment. During the skip phase, however, gases produced by the pyrolysis, the thermal decomposition, of the AVCOAT became trapped beneath the charred surface layer. Under the Apollo program, the AVCOAT formulation had used a manufacturing process that produced a more porous char structure, allowing those gases to escape outward. The Artemis AVCOAT, produced under a revised modern manufacturing process, formed a denser char that gases could not vent. The pressure built beneath the surface. Combined with the mechanical stresses of the skip maneuver itself, the char layer fractured. The interior of the Artemis I capsule remained intact. The crew compartment had not been directly compromised. NASA assessed this. The agency reached a conclusion, and then NASA made the decision that would define the conditions under which 4 human beings would board a spacecraft for the return from the moon. The heat shield would not be replaced. The reasoning was this: if the skip reentry profile was the mechanism that had caused the fractures, if the trapped pyrolysis gas was a consequence of that specific trajectory, not of the AVCOAT material in isolation, then eliminating the skip maneuver would eliminate the failure mechanism. Artemis II would use a steeper, more direct descent profile. No skip. The vehicle would descend in a single continuous arc. NASA had 2 choices: delay the mission, rebuild the shield, and wait, or modify the reentry approach and fly. NASA chose to fly. Critiques raised a consistent objection. The analysis was based on a single data point. Artemis I was the only crewed configuration Orion vehicle that had undergone lunar reentry. There was no second example against which to validate the model. The conclusion that the skip profile was solely responsible was, by definition, not yet independently confirmed. What the crew was told about this assessment before the mission departed, what each of the 4 individuals concluded from it is not. They boarded to account for what occurred at 7:59 p.m. on April 10th. The physical conditions that define that interval require precise framing. The Orion spacecraft returned from lunar distance at approximately 25,000 miles per hour, Mach 32, a velocity more than twice that of a vehicle returning from the International Space Station, which enters the atmosphere at approximately 17,500 miles per hour. The significance of that difference is not linear. Kinetic energy scales with the square of velocity. A vehicle traveling twice as fast does not carry twice the energy. It carries 4 times the energy. The Orion capsule arriving from the moon therefore presented an energy budget that operated in a fundamentally different category from low Earth orbit reentry. Every parameter was shifted. The peak heating rate, the duration of thermal exposure, the deceleration forces imposed on the vehicle structure during descent, all of that energy had to be converted entirely within a specific corridor into heat and then dissipated before the vehicle could survive to lower altitude. As the Orion capsule descended into the upper atmosphere, the air in front of the heat shield could not move out of the way at sufficient speed. It compressed. Compressed air heats at the velocities involved. The process does not stop at hot gas. The air molecules in immediate contact with the heat shield ionize. They shed electrons and achieve a 4th state of matter referred to as plasma. Plasma has electromagnetic properties that hot gas does not share. Among those properties, the capacity to absorb and reflect radio frequencies across a wide spectrum. This is not a communication equipment failure. It is not a technological limitation that better hardware could overcome. It is a direct physical consequence of the state that re-entry necessarily creates at lunar return velocities. At 7:59 p.m. Eastern Time, the Orion capsule entered that condition. The plasma sheath formed. Every communication link, voice, telemetry, uplink, downlink, was severed simultaneously. The external surface of the heat shield at this moment reached temperatures approaching 5,000 degrees Fahrenheit. Steel melts at 2,500 degrees Fahrenheit. The heat shield's mandate was to ensure that the temperature inside the crew compartment remained at approximately 75 degrees Fahrenheit throughout the entire sequence. The margin between those 2 numbers, 5,000 degrees and 75 degrees, is the structural definition of what the AVCOAT was required to maintain. For 6 minutes, no one on Earth knew whether it was doing so. Inside the Orion capsule, the conditions of the blackout period were not experienced as silence. The crew would have observed plasma formation before the communication link severed. Ionized gas at these temperatures produces visible light, an orange-white luminescence visible through the capsule windows. The atmosphere itself in a state of incandescence on contact with the vehicle. The sustained deceleration forces during the direct re-entry profile reached approximately 3.9 times standard gravitational acceleration, nearly 4 Gs, maintained across the full duration of the descent arc. For reference, Aerobatic maneuvers that trained pilots tolerate for seconds at a time sustained that load continuously throughout the entire blackout interval. The flight computers aboard Orion executed the re-entry sequence autonomously. The trajectory had been programmed, the maneuvers were automated, no real-time input from mission control was possible. Not because the communication link had malfunctioned, but because the plasma sheath made transmission physically impossible in either direction. What no automation could control was the behavior of the heat shield under the thermal and mechanical conditions of the direct re-entry profile. A profile this specific heat shield had never experienced, because Artemis II was the first time this approach had been flown on an Orion vehicle. The history of human spaceflight contains the record of what occurs when thermal protection does not perform. In April 1970, the crew of Apollo 13 descended toward Earth, with genuine uncertainty about the integrity of their command module heat shield. An oxygen tank explosion 2 days into the mission had so damaged the service module that engineers could not confirm whether the shockwave had compromised the heat shield mounted behind it. The crew entered the atmosphere with that knowledge. Apollo 13's shield held. On February 1, 2003, the space shuttle Columbia re-entered Earth's atmosphere on its return from a 16-day mission. During launch, a piece of foam insulation had separated from the external tank and struck the leading edge of the left wing. The damage was cataloged. Internal assessments were conducted during the mission. Engineers debated severity. The crew was not fully informed of the range of outcomes that had been identified as possible. On re-entry, superheated plasma entered through the breach. Columbia disintegrated over the western United States. 7 crew members were killed. What distinguishes the Artemis II situation from Columbia is not the presence of a known anomaly. Both involved documented thermal protection damage, identified before the critical event, but the category of that damage. The Artemis I fractures were in the ablative surface material, the material whose function is controlled consumption. The Columbia breach was in the vehicle's load-bearing wing structure, allowing direct plasma ingress into the vehicle interior. These are not equivalent situations. What they share is this: a thermal protection anomaly was documented, an assessment was conducted, a decision was made that flight could proceed, and in both cases the outcome, whether the conclusion was correct, was determined entirely during the minutes in which no external observation was possible. Flight Director Rick Henfling and approximately 1,000 personnel across mission control and supporting facilities had spent months in preparation for this interval. What none of those preparations could provide was observation of what was occurring inside the plasma sheath at 5,000 degrees Fahrenheit above the Pacific Ocean. At 8:05 p.m. Eastern Time, a signal appeared on the mission control monitors. Signal restoration is not by itself confirmation of a successful re-entry. It is confirmation that the plasma sheath had dissipated, that the capsule had decelerated sufficiently to exit the conditions that block transmission. A returning signal indicates vehicle survival to that point. It does not independently confirm structural integrity, crew status, or heat shield condition. The first voice transmission from the Orion capsule integrity following signal restoration was received at approximately 8:05 p.m. Eastern Time. Commander Reed Wiseman confirmed that all 4 crew members were in good condition. The re-entry sequence continued. At the appropriate altitude, 2 drogue parachutes deployed, smaller canopies designed to stabilize the capsule's orientation and initiate the deceleration sequence. At the programmed interval, 3 main parachutes opened. Each main canopy measures 116 feet in diameter at full inflation. Combined, they reduced the Orion capsule's descent rate from several hundred miles per hour to approximately 17 miles per hour at the moment of water contact. At 8:07 p.m. Eastern Time on April 10, 2026, the Orion spacecraft integrity impacted the surface of the Pacific Ocean approximately 40 miles off the coast of San Diego, California. Post-mission reporting described the landing as a bullseye. At the post-Splashdown press conference, NASA Associate Administrator Amit Kshatriya stated, "Flight Director Jeff Radigan said we had less than a degree of an angle to hit after 250,000 miles to the moon, and their team hit it. That is not luck. That is 1,000 people doing their job." The USS John P. Murtha, the primary recovery vessel, was positioned within range. All 4 astronauts were extracted, transported by helicopter to the ship's flight deck, and transferred to the medical bay. All 4 were ambulatory. All 4 were reported in good condition. Mission Control in Houston displayed a single sign as the crew was recovered: "Welcome home, Integrity." The Orion capsule will undergo post-flight heat shield inspection in the coming days. That inspection, the condition of the AVE coat material following the modified direct re-entry profile, is the data point the broader Artemis program required from this mission. It will determine whether the fracture mechanism identified from Artemis I was eliminated by the change in trajectory, or whether damage of a different character emerged from the new profile. It will determine whether the engineering decision was correct, or whether the crew had survived on margins that were sufficient on this occasion, but not yet fully characterized. It is worth recording the factual context against which this inspection will proceed. 2 days after Artemis II launched, the White House released a federal budget proposal calling for a 23% reduction in NASA's operating budget, approximately $5.6 billion. The consequences of that proposal for the Artemis III crewed lunar landing, currently planned for mid-2027, are not yet resolved. What the record confirms, as of April 10, 2026, is that the shield held 4 people who departed Earth on April 1st returned to it 9 days later. What the record does not yet confirm is whether the outcome was the result of the engineering decision, the modified trajectory eliminating the failure mechanism identified from Artemis I, or whether the heat shield performed within margins that were sufficient on this occasion, despite conditions that had not been fully characterized in advance. Those are not the same conclusion. The first describes a problem understood and resolved. The second describes a problem managed under uncertainty and not yet closed. What the post-flight inspection will determine in the coming weeks is which of those two conclusions the physical evidence supports. That is an honest assessment of where the documentation currently ends.